My name is Yondon, and I'm one of the co-founders of Livepeer, decentralized video streaming network. And the title of my presentation today is Compute over Video Data for Web3 Video Streaming. So I'm going to talk about a couple things today. First, I'm going to talk about this term, compute over video data, why I specifically use that term. And then I'm going to go into this CID video streaming playback demo that I think can help illustrate some of these concepts around compute over video data. And then I'm going to dive into a little bit of how it works under the hood. So that demo that I'm going to show you. And then lastly, I'm going to take a step back and talk about what we see as the decentralized storage video compute pipeline. So to kick things off, compute over video data. Unfortunately, this doesn't have as nice of a ring as COD, compute over data, but we'll work with that. And the reason that I think it's interesting to focus specifically on video data for this presentation is because of this graph, where video is eating the internet, where today, 80% of the bandwidth on the online is already video in terms of social media applications, Netflix, basically all the different video streaming applications that everyone spends time looking at when they're at home. And that number is only going to increase over time. So we know that video is important for society, and it's going to be an increasing part of our daily lives. At the same time, video still has unique challenges to scale on the internet. So the great news is that in this day and age, we've learned to scale Web2 apps. I think we more or less know how to scale Web2 apps. There's still a lot of interesting things happening there. But with video specifically, we're still learning how to scale video on the internet in a Web2 context. And it gets even more interesting when we talk about a Web3 context as well, because we're simultaneously learning how to scale video in Web2. And we're also bridging into this new paradigm of Web3, where, of course, scalability is still really important. And a question and thing that oftentimes comes up when it comes to video is, what does it take to build the next YouTube, right? So YouTube is this massive platform with so much data streaming through it every single day. And what does it really take? And oftentimes people jump to video delivery, so being able to deliver video really fast to end users, and that's super important. But if you want to be the next YouTube, you need that and a whole lot of other things in addition to that. So the list here just scratches the surface, but I think it can help illustrate some of the additional things that are necessary in order to do video at scale on the internet. So we have things like transcoding, the process of taking an input video file and translating it into different codecs and different versions and qualities so that it can be played back on multiple different internet connections. We have transmuxing. So similarly, there's different video container formats, which I'll talk a little bit more later on in the presentation, but these container formats are going to influence the types of features that you can implement with the videos and the type of data that you can bundle with those videos when you play it back online. And then we get into more fancy things such as metadata extraction. So videos are great for us when we visually watch them, but what happens if you want to search through them? What happens if you want to make sense of the data that's actually flowing through your platform? Metadata extraction through tools such as AI and extractive techniques for searchability end up being really important. And then we also have things like audio transcription for basically taking an audio stream and converting it into actual text so people can not only read the content, but also listen to the content of a video stream as well. So those are all things that end up being table stakes over time when we talk about video platforms online. And one other thing that's worth noting here that also is a challenge is a lot of the things that I just mentioned here are all forms of compute. And something else that's interesting about video is that oftentimes there is going to be a lot of advantages from a performance and research management standpoint in order to be able to chain all of these things together in a single pipeline on the same hardware. And I'll get into a little bit why that is later on in the presentation. But I want to highlight all these things because these are all things that someone that is building the next YouTube, that's building the next great video streaming application need to worry about. So we want to make sure that those challenges can be tackled effectively for them so they don't have to worry about all these complexities. So ultimately, compute over video data, we just established that video data is not only important, but complex to deal with. So what is the goal of so-called compute over video data? Well, I would say that the goal is support all of the video compute necessary to create the next wave of video experiences on the internet on top of a shared layer of verifiable data that's open and accessible to everybody. And we think that the way that you can enable this, and I think this aligns with everything that a lot of people are talking about in this Compute Over Data Summit, by using CIDs as the reference to original videos so that that can establish this shared verifiable data layer that can be anchored to something like IPFS, but using those CIDs as these verifiable references to original content, and then using them as base ingredients for additional enhanced renditions and videos. So these can be different qualities, they can be filtered versions, and they're all generated on the original content and are created by applying compute on top and applying transformations on top. So I see this as the goal of so-called compute over video data. And in order to help illustrate this a little bit more concretely, because I'm not sure how many people are familiar with some of these like video workflows that I'm talking about, I want to go through a quick demo of a feature that we built recently. But before jumping in, just want to rehash a few things about video transcoding and why it's important, because that's going to be the focal point for this demo. So video transcoding, I've been calling the plumbing of video streaming online. And the reason for this is because we want to be able to watch a video on our Android, on our iPhone, at home, on a crappy conference internet connection. And we want the playback to be smooth no matter what. And we want to be able to watch the same visual content. And here are some of the things that you would care about when it comes to smooth playback. You want short time to playback, meaning that when I press play, I want things to start. I don't want to have to wait 5 seconds and then all of a sudden it starts playing. I want device compatibility. As I mentioned, I want to be able to switch between different devices and watch the same video. I want browser compatibility. You might be a Brave user, I might be a Chrome user, and they might be a Safari user. They should all be able to access the same experience. And we want bandwidth compatibility. So as I mentioned, regardless of where you are, as long as you have a decent enough bandwidth connection, you can still watch the video, even if it was originally recorded in high def 1080p 4K. And you can't do this with a single file, right? Because there's no way that you can address all of these considerations by just uploading a file and saying that you're done. However, you can do this if you do post-processing. So if you send in a file and then you go through this transcoding process to transcode it into different versions that can support different devices, different browsers, different bandwidths, then you can actually get these compatibilities. And also, by ensuring you have this compatibility, you can also get short time to playback because you have the right video for your environment. And by having the right video for your environment, you get things like short time to playback and minimal buffering. So Livepeer is this global and open decentralized video infrastructure network. And what we are very focused on is taking care of these video compute tasks like transcoding and outsourcing it to this marketplace of node operators that bring these resources such as CPU, GPU, and bandwidth so that you have open marketplace pricing and this just is taken care of for you under the hood. We've built this Livepeer Studio product, which is, you can think of it as a gateway analogous to IPFS gateways to the IPFS public network. Livepeer Studio is one of the first gateways to the Livepeer network. And instead of only being focused on retrieving files from a decentralized storage network, it's focused on giving you back transcoded playback video, as well as taking care of other video compute tasks on top of that video as well. So what we worked on recently was something that we identified and noticed is that CIDs are a great standardized reference for content online. Because of the verifiability, you can establish these verifiable links between data and identifier because it's just a hash. However, as I mentioned earlier, if you're just throwing a video file into the ether and throwing it into IPFS, in some cases it can turn out okay, but once you start dealing with 2-hour-long video podcasts, different formats like portrait style things that are uploaded from your phone, you start getting into this really hairy support matrix of, well, it will work okay if you're in this situation, but it's probably not going to work very great if you're in X, Y, or Z other situation with this amount of bandwidth with this device. So the feature that we built was a combination of a pipeline in Livepeer Studio that can take a CID and then pull the data in, send it through the network, go through this video transcoding process and make it available for playback. And we combine that with some easy to use JavaScript tools where you can drop in a player, drop in a CID or an IPFS URL, and then all of that is taken care of for you under the hood. And what happens is that that CID is maintained as the reference to the original content, and what you're asking of the player is give me the best possible experience for this CID, and give me the best possible experience by applying this transcoding process to it. And then the transcoding process creates these transcoded renditions, and you get better playback. So I'm going to just narrate a quick demo that can hopefully illustrate how this works. Hopefully this. All right. So we'll fast forward a little bit. So the prelude here is I went into my browser and I'm trying to simulate a mobile connection, a mobile 3G connection, because the goal here is to show what video playback would look like directly from an IPFS gateway versus through that feature that I just mentioned. And it's a lot more interesting when we're talking about mobile connections, because that's when you see the most bandwidth fluctuation. So here we try playing a video file directly through the gateway, and we can see that it loaded and now it's buffering. Right, and this is because we're on this mobile connection and we just can't pull the data in fast enough. It really doesn't matter how fast the gateway is in this case. It could be the fastest gateway in the world, but if our connection can't actually pull data fast enough, we're gonna need to continue pausing until we can fill up the buffer of the player so that we can keep playback going. In the meantime, if we switch over to this new docs page that demos this CID playback feature, we can drop in an IPFS URL with the CID, and this should give us a better playback experience. So if we give it a second, I'm going to input that IPFS URL with the CID. So that's the same CID as the previous video. We're going to press play, give it a second. And there we go. We start playback. And what we'll notice here is that it is going to continue going with no buffering, same exact video, except it's been passed through this pipeline. You can't really notice it this well here, but if you were on like your own laptop and looking at this, you would be able to notice that it's slightly downgraded in terms of quality, not substantially, but the idea there is you're watching a different version of the original video because it's been transcoded, and you can switch between these different versions. So that's the demo of the feature, and I'm going to move forward a little bit. And now I'm going to talk a little bit about what's happening under the hood. And in order to explain that, I'm going to start by describing what the network is doing and what this studio product is doing. And then I'm going to go through a few video concepts that hopefully can provide a good enough background as to the types of compute that are actually happening when we talk about this feature. So at a very high level, when a user uploads a video to Livepeer Studio, that gateway, it can come in two forms. If it's a live stream, you might be using a protocol like RTMP or SRT. If anyone has ever streamed on Twitch and has used a piece of software like OBS, which all Twitch streamers are familiar with, this is what the data ingest format would look like. You would use a broadcasting tool, it would send out RTMP or SRT, and then that would go to some server somewhere. Alternatively, if you have a static file, and you're doing YouTube-style uploads, it might be an MP4 file or MOV file, you would just upload that straight to Studio. So that's the entry point. User somehow ingests video into Livepeer Studio. And then from there, this is where the handoff to the network happens, where the network has two types of nodes. We have broadcaster nodes and orchestrator nodes. And orchestrator nodes are the ones that are responsible for the heavy lifting. So the transcoding process that I talked about, that's something that they're responsible for because it's actually very compute intensive. And I'll get into a little bit as to why that is momentarily. But for now, you just need to know that transcoding is pretty compute intensive, and oftentimes hardware acceleration can speed things up a lot. So orchestrators are typically going to be well equipped with hardware, likely GPUs. On the other side, broadcasters, they are the ones responsible for some of the preparation of the video and things such as discovery and selection. So the broadcasters are the ones that are going to receive that video, route it on the network based on discovery and selection algorithms, piece together the video that comes back, and then make it available to the end user, and then that gets relayed back through Studio to the end user. So that's a high-level description. I think what might be helpful for anyone that hasn't spent a lot of time thinking about video tech is actually get into what is happening when we talk about transcoding. And I'll go through this at a high level in the next couple of slides. So a good place to start is video codecs. So a video codec takes care of or describes two different processes. One is decoding and encoding. So people are probably familiar with codecs in other contexts. Similarly here, you need to be able to decode formats and encode into new formats. And video codecs are specifically dedicated to tackling this hairy problem, which is, as is, if you just talk about video, over the past couple of years, everything keeps going into higher and higher resolutions. We keep getting better and better quality. And then video is information over time, right? And we have all of these frames that need to be played back at really fast speeds in order to simulate and indicate motion. So that's actually a ton of data. That's a lot of data without any post-processing. So the image on the left basically illustrates what would happen when you use a video codec, where you have a video codec in order to decode and encode the video, and you might also have an audio codec, and that similarly is responsible for doing something on the audio in order to take it from one format and one size into another format and another size. And there's this really great article online called H.264 is Magic. And H.264 is one of the most popular video codecs in the world. It's not the only one, but at the moment, it's still pretty industry standard amongst video streaming providers. And they presented an example in this article where they had this original video that was captured at this random resolution. The actual resolution doesn't matter. But the reason that we care about the resolution is we can make an estimate of, given this resolution, the amount of time a video would play back and the frames per second of the video, how much the bit rate would be and how much bandwidth you consume. So in this example, 5 seconds of this 60 FPS video, as is, not doing anything at all, would be 1.2 gigabytes. That's 5 seconds. That's pretty insane, right? Like most people, even if they have a great internet connection, and the reality is most ISPs aren't that good, like if that was what you would be downloading, that would just straight up not work. But that's why we have video codecs, and that's why video codecs were invented to begin with. And with H.264, with some preset settings, you can actually shrink that 1.2 gigabytes into 175 kilobytes, which is pretty insane, right? So in that example, it's not always going to be this case. It depends on your parameters and how you tune it. But these are the types of magnitudes decreases of data size that you would expect from using some of these video codecs. And in this example, it's like a 10,000 decrease, 10,000x decrease in the actual size of the video that you have to pass through into the bit rate. And that's why video is able to work on the internet. If you weren't doing any of this compression, video would not work at all. And the reason that you can get these magnitude improvements is because video codecs actually tend to be lossy, unlike image codecs. So if you remember, what I was talking about was you have all these frames of images in succession to simulate motion. It turns out there's a lot of redundant data there. So what these codecs do are they try to make intelligent decisions about data that they can toss out, and you wouldn't notice the difference because the human eye can't really tell the difference between this amount of data and this other amount of data. So those are video codecs. Video containers, I'll touch briefly on because it's relevant. What you need to take away from this slide is that there are way too many containers to really even consider. And all these containers have different features and are appropriate in different contexts. And for now, for this presentation, we'll focus on a container called MPEG-TS that just happens to be one of the most popular containers for video streaming online. But the important takeaway here is that containers are the way that you bundle multiple data sources together, and they also have specific video codecs that they support. So going back into the previous slide, you typically couple a video codec with a video container. Going forward, now we get to something called HLS, which is HTTP live streaming. This is a little bit of a misnomer in that it was originally created for live streaming, but now is used for on-demand video as well. And this is actually the most popular way to deliver video online on the internet. So if you use platforms like YouTube or Twitch, under the hood, when you get delivered video, it's typically in this format and in using this standard. And basically, what the standard describes is that you can describe a single stream in the form of a playlist, and then that playlist can link you to multiple sub-playlists, oftentimes called rendition playlists. And those rendition playlists represent different versions of the same video that you can switch between dynamically as a video plays back. And this is what these playlists look like. It is probably a little bit hard to read this. I probably should have made this bigger, but I'll just narrate a little bit. On the left, you have the master playlist. It's an example, and I just use a curl command to fetch one of these playlists, and what you would see in this playlist are references to the other rendition playlists. So the name of the master playlist is index.m3u8, and it has references to source.m3u8, which is the source rendition. This is the original content untouched. Then you have, for example, 480p. .m3u8, and that's the 480p version of the video that you can switch to if you need to. And then on the top and the bottom, it's a little bit hard to see, we have the source playlist and the 480p playlist. So looks pretty similar on the top and bottom, and the only difference is that the top is gonna reference the content in the actual video chunks for the source, and then the bottom is gonna reference the actual video chunks for the 480p version. Putting this all together, now that we have those playlists, why do we have those playlists in the first place? Well, what's nice about those playlists is that it basically has this directory, and then that directory has subdirectories, and then what a video player is going to do is it's going to say, well, you've been able to download data this fast for the past 5 seconds. So based on that, I estimate that your available bandwidth is X. Given the available bandwidth, I'm going to look at these directories and look at these playlists and try to decide which is the best video version for you. And that happens throughout the playback process. So if you go to YouTube, that's why they have this switcher available that allows you to switch between those different versions. And this illustration on the right just gives a high-level overview of that. And the reason that this is possible is because the player is pretty smart. So unfortunately, we can't use something like an HTML5 video tag for this type of playback because HTML5 video tags don't have support for HLS in all browsers. They're actually only supported natively in Safari and Edge. There's a whole story about why that is, and if you're wondering, basically it's Apple's fault, and I'll leave it at that. But in order to support HLS playback, we need JavaScript. So JavaScript players are required for all of these browsers, and basically they use this special media source extension browser API in order to handle these types of formats. And then there's open source libraries for this, such as HLS.js and Video.js. So putting that all together, that is some of the stuff that is happening under the hood when you saw that CID video streaming playback feature, where given a CID, we pull the video in, we pass it into Studio, Studio passes it to the broadcasters that then route the work to orchestrators, and then the work that's being done is we take the MP4 file, we translate it into HLS multivariant playlists, we have transcoded versions of the video, and then now we can switch between them in a player in the front end in the browser. Just to wrap things up here, a couple things that we're looking forward to going forward in the future is that we can do some more interesting things here, especially with CIDs. So we could do something like CID playlists. So the playlist that I showed before had just regular HTTP links to a server that's serving that content. But because these playlists can point to anything, in theory, we can actually replace all those HTTP links with CID references as well. So what's cool about that is that when we replace all of those links with CID references, the player is kind of smart already, right? The player is already doing all these things for you. Well, the player can also do things like choose how to resolve a CID. So I can resolve, for example, certain CID references in the playlist using one method, using a list of gateways. In the future, when decentralized CDNs are more performant, you can also resolve the CIDs using that. And then now you have this flexibility that you can use these CID playlists in order to support that type of fetching and dynamic resolution methods. Something else that we look to in the future around this feature is something called Trustless Muxing. So if you recall earlier, Muxing is the process of taking a video and basically repackaging it into a different video container. But what's actually interesting about this form of computation is that it doesn't touch the actual raw content of the video, but it does change the video file as a whole, because you can think of it as taking something that's been wrapped up and changing the wrapping around it. If that's the case, something that we could theoretically do is, instead of taking a CID of the actual entire video file, we can take the CID and take the hashes of the raw media content, so not the entire thing, but the actual inner content of the video file. So these are things like the video track, the audio track, metadata track, timestamps. And then now we can uniquely identify and verify the raw content within a video file. And then when someone transmuxes it and changes it to a different container format, we can verify ourselves and confirm that they didn't touch the inner contents of that video. And then the player can be smart enough to say, well, you told me you were giving me an MP4 file. This container makes no sense. And I can also check that you didn't touch the inner contents of the video as well. So we think that can be pretty cool, and that enables this enables a flavor of video computation that can be completely trustless, because we can do these small tricks with CIDs and choose selectively what data we're computing the CID over. Okay, so that's how the CID video streaming playback feature works. And to close out this presentation, I'm just going to take a couple of moments to talk about the decentralized storage video compute pipeline. So we were very much focused on transcoding and transmuxing in that feature and the previous part of the talk. But what's interesting is that there's a whole lot of other things that we might be interested in doing once we have a video in this pipeline. Just some examples to go over here. We could do things like neural network-based audio transcription, where video comes in and you can extract captions from it and then insert it into a new video that you can then play back online. You could do things like video restoration, also using neural network models, where you can upscale and increase the resolution of a video that was grainy in the past. An example on the left shows some of the things that you can do there. Some more forward-thinking things is with the whole generative AI craze. Instead of thinking of the input of a pipeline being video, you can think of the input of a pipeline being text. And you can take a generative model, like a stable diffusion-based model, do text to image. You could generate a whole sequence of images, and then you can also, within that pipeline, concatenate all those images together and then encode it into a video stream. And the image on the right is actually an example of a video that I created. I'll skip over the playback for now in the interest of time, but just an example of some of the things that you can create there. And what I really want to illustrate with those examples is that as we expand the number of applications that are being built, not only in Web3, but generally going forward in the future, we can build a lot more interesting experiences once we have videos in these pipelines. So examples here, video input comes in, you can decode it, scale it, transcribe the audio, encode it into a new video, stream it online. On the bottom, you can take a piece of text, you can generate images, concatenate them together, encode it, send it over the internet, and stream it online. So all things that are possible with this pipeline. And all of this can still remain rooted in original references to source content through CIDs. So CID of a video input or any piece of text comes in, we apply compute on it, and out comes enhanced video. Ideally, we can have this pattern around verified input in, verified output out. So there is this question of, in this world where we create all these enhanced renditions and versions of the same video, how do we link the video output of the pipeline back to the input, right? So if I apply X, Y, or Z transformation and I end up with this cool new enhanced video, how do I go back to the original CID and say that those two things are actually related? Some of the things that we're thinking about here, we generally think about this in terms of like pipeline provenance. And some of the things that we've been thinking about here is each stage of the pipeline is a transformation. What if each transformation also has an input CID and an output CID? And you continue doing this all the way down through the rest of the pipeline. And then each transformation results in assigned attestation over the input CID, the output CID, and some metadata about the executor required for audit or reproducibility. And if you have that, you can start imagining this audit trail and provenance chain going back to the original CID. And ideally, this is something that can come attached to the media files that are passed around so that you can always go back to a verified input. So not only do you have a verified input, you have a verified output now because you can link it all the way back. One thing to note here is that because this is a media pipeline, it's likely that the CIDs in the middle of the pipeline are actually going to need to be calculated over decoded frames, so the actual raw content. And the reason that I mentioned that is, I'll get into this a little bit in challenges. So those are some of the things that we're thinking about and ideas that we're exploring right now. I'll start with the one on the bottom, where we need to be thoughtful about how to structure these pipelines, because there are big performance advantages of keeping data on the same hardware for all stages. And the reason for this is, if you revisit the slide that I was talking about with video codecs, video without decoding it, well, video without encoding it is gigantic. But in order to apply transformations to the video, you need to decode it first. So in these pipelines, if you go back to one of my earlier slides, you would have noticed that everything with the video input starts with a decode step, and that's because you need to decode the video and basically open it up so that you have access to the underlying frames. So my point with the pipeline here is that if you try to split the pipeline in the middle and say that, well, someone was responsible for scaling and I want to pass this to another machine, that is decompressed frame data that would need to pass through pipes in order to get to that other machine, and that's going to be a really large amount of data. So that's one of the big considerations here, where when you look at a lot of these like GPU and hardware-based flows, they try to keep things on the same machine, because once you start leaving that machine, you start incurring high bandwidth costs, like PCIe bandwidth costs. If it needs to transit through a network, bandwidth costs there as well. So that's one consideration. And then the last thing that I'll mention here is determinism is tricky as well. So it's common for video codecs to give flexibility for encoder implementations that lead to non-determinism. So they say things like, as long as you fulfill these guidelines, you can make any decision that you want, and you can actually do whatever you want, and that results in encoders making these different decisions, and it results in different outputs, bit for bit. So you actually see this. So the fastest decoders and encoders on the market right now are hardware-based, stuff like NVIDIA's NVENC and NVDEC. And yeah, they're going to have different outputs for the same settings with each generation. So those are some of the tricky things to consider here as well that we're thinking through. So with that, I think basically, to sum things up, what I went over is this notion of compute over video data, why it's important, why it's interesting, why it's important to tackle, an example that hopefully illustrates some of the things that you can enable with compute over shared verifiable video data in the form of CIDs, a little bit of how it works internally, and then lastly, a little bit more of a forward-thinking process around this decentralized video compute pipeline that we're starting to work on and starting to ideate. So if any of these topics are interesting to anyone here, would love to chat more about any of the challenges, or just if you want to learn more about some video stuff and what it has to do with CIDs and verifiable decentralized storage. Thank you.
Hey, thanks for that great talk. Two questions, if you don't mind. One is a bit more sort of random and general. A lot of video, audio related stuff has DRM related metadata in there to prevent people from playing. Yeah, obviously, you know what it is. Have you thought about where that fits in to the decentralized philosophy of everything being open and available?
So two immediate thoughts there. One is that people are going to continue to have those types of requirements around DRM and rights management. And I think there are ways to handle it. So we already see certain protocols in this space. So not us specifically, but what we try to enable is for developers to use other protocols and other tools that can help kind of secure content in transit before it gets processed and after it gets processed. So there are protocols that can help support with dynamic access control, where the video content goes into the pipeline, encrypted, it gets decrypted, goes through the processing, and then when it comes out on the other side, it's re-encrypted, and then the only people that can decrypt the content in the browser would be if they fulfill some set of access control conditions. So I think those are examples of ways that people in the space are trying to navigate that right now, and I expect that to continue to happen. The other reaction here is that at the same time, something that I'm personally excited about is just more and more experimentation with like Creative Commons licensed content, which we're seeing a lot of, especially in the NFT space. Now, I mean, we'll see where that goes, but I think there's a lot of interesting things that you can start doing when you actually have these open data treasure troves that people choose to Creative Commonly license them and then allow people to freely remix and create experiences around it. So I think that's the other thing worth considering, where, don't get me wrong, people are going to need the former and people are working on that, but I think there's going to be a lot of exciting stuff that comes from the latter as well.
Okay, thanks. And the second question, can you tell me a bit more about the underlying network that actually does the transcoding, and specifically where you think Bacalhau might fit in to fulfill the need for computation?
Yeah, I think I started talking about this with some other Bacalhau folks the other day, and definitely this is just like initial reactions, but so the orchestrators, as I mentioned on the network, they do more heavy computing, which is typically going to, you're gonna want it to be hardware accelerated, because hardware accelerated transcoding is just super, super fast. So in a world where, Bacalhau had a lot of GPU fleets available, then that might be a good fit for like running some of this orchestrator software that we have. So that's one thing. If that's not the case, there is potential other use cases there where it is the case that hardware accelerated transcoding via GPUs is super fast and way faster than CPUs, but it's not without its trade-offs. So one of the trade-offs there are that it's very good at, because it's very good at like certain types of transcoding, but it might not be able to support all types of inputs that you throw at it. So traditionally in the space, that's when people choose to fall back to like CPU and software-based transcoding, which is slower, but you just have more room to program around these edge cases. So something that might be interesting for Bacalhau is like in scenarios where, let's say that this network of orchestrators, it's super fast for all these inputs, but it encounters these edge cases where they can't handle. Right now, what someone would do is just fall back to CPU, but that might be something that perhaps if Bacalhau has support for it, you could fall back to someone that just like spins up a Bacalhau node and can run like a CPU transcoder with the resources available. That's another thought. And yeah, maybe I'll leave it at that, and then there's probably other things that we could talk about, but hopefully that is a good start. Hey, yeah.
Sorry, I missed most of your talk. Big fan of Livepeer, though. One thing that we've been looking at recently with these kinds of like orchestrator nodes is that you can kind of mix two types of incentives. So obviously staking and like having a financial penalty if you misbehave is obviously a really good way to do it because you get mission critical kind of infrastructure. The other thing we've been experimenting with is layering reputation on top of that as well to kind of give a boost to nodes that are consistently honest, which like over time should theoretically reduce the number of replicated compute cycles and make the whole network a lot more efficient because you're not auditing people, so you don't have to check their work. Have you guys looked at that side of things at all, or any insights?
We've definitely talked about it and are very interested in digging further there. It's not something that so what I'm about to describe, we don't have out, but I think it's an interesting area of exploration where, I mentioned that these broadcaster nodes are responsible for making these selection decisions, and right now the selection decision factors in a few considerations such as the amount of stake that you have, your pricing, so on and so forth. Something that we've talked about and considered is because there's all these different factors that you care about when it comes to routing jobs on the network, like creating these utility scores that can take a set of inputs and weight each of them, and then create a weighted utility score that can then be used for selection purposes. And then it just becomes like how you choose to weight that utility when you make the selection decisions. And then it can incorporate things like stake, pricing, but also historical reputation, where it is the case that the broadcaster nodes are keeping track of performance metrics over time. You can think of it as like a smart agent that just like always tries to remember like how good were you in the past hour or so, and that can help influence whether I'm going to continue selecting you going forward, and that's going to affect your revenue. So we think that is an interesting area to dig into, where taking all these data points that you care about anyway, that you want to gather anyway, and then basically inputting them into these utility scores, and then just treating it as a potential optimization problem, or there's like other like numerical methods that you might want to use there. So that's the extent that we've thought about it. So I guess a little bit tangential to what you were saying, but we imagine reputation could be incorporated into that. Yeah.
Hey, thanks for that presentation. When did video mining go live, and what's kind of the size of the economy so far as like revenue and the trajectory that you're seeing?
So the network launched in 2018, but I wouldn't say that there was a substantial amount. So the hardware accelerated transcoding, so a lot of what I've talked about only became supported, I think, in like 2019 or something like that. So that's probably the date that we would want to go back to. So that's the first question. Regarding the size of the network today, I think off the top of my head, I think we were averaging, somewhere around like 2.7 to like 3 million minutes of video transcoded. I forgot the unit. I think it might have been, Shannon might know. I think it was either like per week. I think it was something like per week. Yeah, and then in terms of revenue, in terms of fees, that mapped to something like, I think right now anywhere between like 10 to 15K a week as well in USD terms. So relatively speaking, it's still small, right? And we're still trying to grow the network, but that's where it is today.
Sorry, follow-up question on that one. You mentioned GPU cycles before and like how that's kind of a key element. Can you comment on profitability for people that are running these nodes? Like, have you looked into that much, or are they mostly doing it out of goodwill or supporting the network at this point?
So I think it'll definitely vary from node operator to node operator, but I think on average, for someone that already has the GPU, like they pay the fixed cost of that, we do think that it is definitely profitable for them because they pay they just pay the marginal cost of electricity at that point. And for that reason, historically, we have a decent amount of operators on the network that come from a crypto mining background. So the fixed costs of the GPU are already paid for. And they weren't actually using the on-deck video encoding, decoding chips to begin with because you don't use those for any of the mining stuff. You just use the CUDA cores. So those were just sitting there unused to begin with. So our whole thing was giving them that additional source of revenue where they incur the marginal cost of electricity for sure. But in terms of the actual revenue that they would get from using those encoding and decoding chips, it would surpass that. The variability here comes in bandwidth though. So it's not as high bandwidth requirement for something like a retrieval miner in one of these decentralized CDNs, but there is a bandwidth requirement because you still need to funnel the video back out to whoever is requesting it. So that's where, depending on where you are, that's something for the operators to consider, like what is the bandwidth cost going to be for you. But I think from a hardware standpoint, assuming you've paid the fixed costs already and you're coming from one of these backgrounds, it should be profitable today.
One last question for you, if you don't mind. A lot of us in the community are building out various networks of workers or compute servers and these sorts of things. And it seems like you guys have been through a lot of growth and a lot of learnings probably over this past time, growing the community, marketing the community, attracting people to participate. Are there any takeaways or lessons learned from your guys' experience that we should think about in terms of just how we would approach building up the supply of workers, things that worked well or that you would do differently?
Yeah, I mean, the first thing that comes to mind is so it was interesting that previously you mentioned that you asked whether a lot of people are doing this out of goodwill. And we also have, I wouldn't describe it as doing it out of goodwill, but we definitely have people that are, they care about profiting, but they also care about kind of helping establish the infrastructure and foundation of this network from ground up. And that ends up being super important because even though they still need to be profitable, those members of the community have been invaluable for helping spur further supply side growth. So much of this activity happened. So a lot of people do keep things close to themselves, but that's always going to be the case. But you can still encourage a mix of that and people that also contribute back to the community. And then as long as you have a select number of people like that are kind of champions of the community, it helps a lot from a supply side growth standpoint because then it's like you as a team, of course you want people dedicated thinking about how you can grow the supply side, but now you have all these other people that deeply care about it as well. And they also deeply care about bringing more demand on the network. So I think that has been something that has been pretty valuable. It's probably still underrated when it comes to building out these types of networks. Like at the end of the day, like, yes, they need to do good work on the network, and at the end of the day, they need to be high quality workers. But especially in these early days, they're also community members that are invaluable to helping grow and kind of establish this thing in the first place. So yeah, that's what I would say. Yeah.
Hey, I'm Shannon. I'm head of ecosystem growth at Livepeer. Joined a year and a half ago. Once you find those individuals who are super passionate about the mission, and definitely when I first joined, I joined as head of community and met with a lot of the individual independent node operators, and yeah, definitely heard from them that they were willing to run at a loss because they cared about the vision. And then it's really empowering those individuals to give them roles to, further understand why they care so much about your project, create space for them, and really amplify their passion.
Brilliant. Thank you guys so much.
All right. Thank you.